Good afternoon. Thank you for the opportunity to present our research. We are a small team from the University of Aizu, Japan. This work introduced firstly Triada, a co-designed algorithm and architecture that accelerate multilinear tensor transforms. And secondly, ISOP, incorporated in Triada hardware mechanism, enabling efficient sparse execution. Together, they target both dense and sparse tensor workloads in modern AI and HPC systems. There are two fundamental challenges. First challenge, dense tensor transforms have extremely high arithmetic and memory complexity. Multilinear transforms grow exponentially with dimensionality, and applying parallelism to reduce computing time proportionally increase energy consumption by increasing both the number of processing elements and communication between them. Second challenge, sparse tensor workloads, very common in AI and HPC, contain 50–90% zeros. Current accelerators struggle with such structural sparsity, often wasting energy. Our goal is to deeply accelerate multilinear transform with hypercubic complexity in linear steps, efficiently supporting both dense and sparse modes. Tensors represent data with multiple modalities, such as space, time, frequency, channel, or embeddings. Each axis captures independent mode of variation, and multilinear transform operates separately on each mode. This structure is essential for understanding how to decompose and accelerate high-dimensional data. Because transforms act independently on each axis, we can process X, Y, and Z modes separately. Triada leverages this property, allowing multilinear transform to be executed as succession of simple linear sweeps. The central operation is a three-linear or three-mode transform, a sequence of mode-wise transform along X, Y, and Z dimensions. This formula describes a family of trilinear transforms such as Fourier, cosines, Walsh-Hadamard, and others, by using different pre-computed transformation methods of coefficient. Trilinear transform converts the input tensor from one system of coordinate to another system, for instance, from time to frequency domain. Initially, three-dimensional transform has six-dimensional coordinate or index space with arithmetic complexity order of n in power 6, scalar multiply, add, combine, or mark operations. The separability of trilinear transform reduces complexity from six-dimensional to four-dimensional by execution of three chaining linear transforms or stages along each dimension. Simultaneously, this reduces arithmetic complexity from n in power 6 to n in power 4. Each such four-dimensional linear transform is matrixed by tensor multiplication. This reduction is based on different tensor partition or slicing, converting execution of matrix by tensor multiplication into multiple of matrix by matrix multiplication with shareable coefficient matrices between slices. We represent three-mode transform as three sums of outer products. We extend classical outer product as broadcast of two vectors to update a matrix to broadcast vector and broadcast matrix to update full tensor. Matrix broadcast is synchronized with a vector broadcast by tagging diagonal elements of the coefficient matrix, while stage 1 linear transform and stage 2 bilinear transform can be implemented within one form of tensor slicing, now, for instance, horizontal as shown on slide. The final stage 3 requires switching to alternative form of slicing to include a missing direction, as shown lateral slicing. Four-dimensional algorithm stages are still not ready to be directly implemented in 3D physical space. Therefore, we are mapping index spaces of those three stages onto the same three-dimensional processor array, converting direction of summation into time. We use the linear or isomorphic 4-dimensional to 3-dimensional mappings, which keep the same metric in algorithm and processor spaces, maximizing efficiency. Triada is abbreviation, 3-linear algorithm and isomorphic device architecture. It consists of tensor core and 3 actuators. Tensor core is a grid of processing elements interconnected in 3-dimensional space. 3 actuators stream mode-specific coefficient into processor core. Triada executes 3 in-place stages in linear time, achieving 100% efficiency for dense data. Each processing element in tensor core combines compute, storage, and communication. Each processing element connects to 3 orthogonal global buses X, Y, and Z, forming 3-dimensional crossover mesh. 3 actuators inject coefficient along each mode. Execution is fully data-driven and index-free. Processing elements react only when operands arrive. ISOP is abbreviation of elastic sparse outer product, is the key mechanism for sparse workloads. Tag-based streaming of coefficient metrics from the actuators divides all processing elements in tensor core into broadcasters and receivers. Broadcasters processing element emit their local values only if they are non-zero. Receivers update local value only when 2 non-zero operands arrive. It dynamically reduces computation, communication, and energy proportional to sparsity. This diagram shows how a single processing element behaves under ISOP. Zero suppression happens at the actuators and at the broadcaster processing element. Receivers processing element never see zero value at input. They simply wait for meaningful operand pairs. This naturally reduces the number of MAC operation, inter-processing element communication, and energy. Here we quantify ISOP impact by using 3-dimensional cosine transfer as a benchmark. A dense 8x8x8 DCT transform consumes about 8.6 nanojoule at 0.7 picojoule per MAC operation. At 50% sparsity, the energy halves. At 98% sparsity, Triada achieves 64 times reduction, reaching only 0.13 nanojoule or about 0.01 picojoule per effective MAC. This demonstrates true sparsity proportional energy scaling. So this slide shows the comparison with state-of-the-art accelerators. GPU and TPU are optimized usually for dense matrix-matrix multiplication, while Triada for matrix-tensor operation. GPU-TPU sparsity support is limited or relies on structure. Triada is sparse native. It cost scales with the number of non-zero operands, not the tensor size. Thus, Triada complements dense accelerating in hybrid pipelines. Triada fits naturally as a coprocessor for sparse and multilinear tasks. Dense operators may stay in GPU-TPU, while sparse or 3-mode transforms migrate to Triada. This reduces system-level energy and increases throughput without replacing existing accelerators. To summarize, Triada accelerate linear, bilinear, and 3-linear transform in linear number of steps. ISOP converts sparsity directly into energy saving. Triada ISOP turns what is traditionally a limitation on structural sparsity into opportunity for energy-aware performance scaling. The architecture is simple, scalable, and flexible, enabling efficient, dense, and sparse processing with one unified framework. Future direction include hardware prototyping, integration with GPU-TPU pipelines, and applying Triada for more tensor modalities. We also plan to extend the model towards the wider multilinear algebra operation, and we open for cooperation as well. Thank you very much. I will now take the questions.